Today's video we'll discuss reaction of alkyl halides. Alkyl halides undergo major three reaction. Number one is nucleophilic substitution reaction. Subtype is SN1 and SN2. Elimination reaction number two, E1 and E2. And third, but not the least, is reaction with metal. Before going into detail, I will discuss in short what is nucleophilic substitution reaction. Nucleophilic means a substance, a species that has affinity for a positive charge, that is nucleus. So it will have some excess electron, like hydroxyl ion, halide ion, cyanide ion, and some species which has excess lone pair, extra lone pair, like ammonia molecule. So these are the general reaction, general pattern, general discussion, means example of nucleophiles. Now in a reaction, when a nucleophile substitutes another nucleophile to form a new product, the reaction known as nucleophilic substitution reaction. Example, methyl bromide plus or reacts with potassium hydroxide in water, aqueous solution. The product will be methanol and potassium bromide. This is nucleophilic substitution reaction. Nucleophilic substitution reaction is of two types. SN2 bimolecular, SN1 unimolecular. You first see the nature of the alkyl halide. It is 1 degree. So from one side the bromide ion leaves, from other side hydroxyl ion enters or attacks. At a point of time both the molecules are uniform with the central alkyl molecule. This is called bimolecular. Another is SN1. Consider now a carbocation with alkyl halide with 3 degree nature. So from the back of from any side other than front, it is not possible for the hydroxyl ion to attack because it is already occupied. This is called static hindrance. So it has to wait for the bromide ion to leave. And then only it gets from this side. This is unimolecular. Now look at this board. Types of nucleophiles. What is that? There is a scale. Iodide less than bromide, less than chloride, less than fluoride, and less than hydroxide. It means hydroxide is capable of replacing fluoride, fluoride capable of replacing chloride, and so on. And so on. So this is the scale. Now see, this scale depends major on two factors. One is charge density, another is basic in nature. Now what is charge density? Charge density means here everyone has unit charge, -1, -1, -1, -1, -1, but see the volume, the largest volume is here, followed by bromide, followed by chloride, followed by fluoride, and last but not the least it is hydroxide. So charge density here minimum, and there it is increasing. Now higher the charge density, higher its basic nature. That means hydroxide can produce more basicity than iodide. Lower is its leaving tendency. That means less the charge, it has more tendency to leave. That means iodide can leave much earlier than bromide, and so on and so on. These two factors will decide the nature of the nucleophiles. Now, types of solvent. Main two types of solvent are used. One is aqueous KOH and alcoholic KOH. This aqueous KOH will help in substitution reaction, and alcoholic KOH will help in elimination reaction. See, aqueous KOH dissolve in aqueous, in water. So all the KOH molecule will be hydrated accordingly to great extent and will cause the dissociation of potassium hydroxide into K plus ion hydroxide ion. At the same time, the alkyl halide molecule contains bromide, Br, and alkyl group. So these are the picture now. Hydroxide ion is more basic. It's a very poor living group. It will always try to be in association with some others. Whereas bromide is easily living group. So what will happen? This hydroxide ion will attach to this alkyl halide, alkyl group, because once the bromide is left, it will be carbocation, and this will be attached to this, and so the product will be alcohol plus KBr. Understand? So in aqueous KOH, this will be the reaction. But in alcoholic KOH, lack of water molecule, there are so less hydration. Less hydration means KOH will not undergo readily dissociated. Rather, the alcohol molecule will be the alcohol molecule will be protonated, and this protonated alcohol will lose water molecule, is a very, very strong living group, leading to production of alkoxide. This alkoxide is a strong base. Now this is so strong that it will attack the beta carbon to abstract hydrogen from it, making a double bond. So see, due to the presence of this alkoxide group, the reaction patterns change from substitution to elimination. But one thing, this solution does not contain alkoxide only. It also contains certain hydroxide. So this is the general mechanism for alcoholic KOH. Now we will discuss the effect of temperature on this substitution and elimination reaction. See, we know the standard formula delta G should be equal to delta H minus T into delta S. Now see, in substitution reaction, an alkyl bromide reacts with aqueous KOH to produce alcohol and potassium bromide. So total number of molecules were 2 and new molecule also 2. In elimination reaction, you see, this is ethyl bromide plus alcoholic KOH and heat. You get ethene, potassium bromide and water. So double bond compound. So here it was 2, but here it is 3. That means entropy value increases. Once the entropy value increases, the delta G becomes more negative, because it will be more negative. As a result, the reaction will be forwarded. So temperature of the solution will increase the elimination reaction little faster compared to substitution reaction. Now, nature of the carbocation also decide the rate of reaction for elimination as well as substitution. Race condition is same. Now see, for elimination reaction, 1 degree less than 2 degree less than 3 degree. You now see the board. This is 1 degree carbocation. Here only 1 beta carbon and only 3 beta hydrogen, whereas it is 2 degree, 2 beta carbon, 6 beta hydrogen, and it is 3 degree which contains 3 beta carbon, 9 beta hydrogen. So number of hydrogen increases from 1 degree to 3 degree. Show the stability. So automatically elimination reaction will be supported by 3 degree carbocation or 3 degree alkyl, because more numbers of possibility to eliminate hydrogen to make double bond. So 1 degree should be less than 2 degree, should be less than 3 degree for elimination reaction. Whereas for substitution reaction, the rate is just reverse. 1 degree should be greater than 2 degree, greater than 3 degree. Now for substitution reaction, the main important point is the ease of substituting point. For 1 degree, the minimum steric hindrance or practically nil steric hindrance. For 2 degree, it is little more, and for 3 degree, the steric hindrance much more. So, the steric hindrance, we can say, is a volume of the space, but to some extent, the charge steric hindrance is also there, which we shouldn't consider. So, for substitution reaction, it is 1 degree, should be greater than 2 degree, greater than 3 degree. So, this is the general pattern for elimination as well as substitution reaction. So far we discussed, it is the nature of solvent, then it is the temperature, and third it is the carbocation that will govern the elimination reaction as well as substitution reaction. So far today's class is over. If you feel it is worth, please pass comment, like, share and subscribe my channel so that I will come with newer and new videos studies for you. Thank you very much.